Okay, type let's consider turbine or compressor. We can represent a compressor by this representation. Flow is coming at pressure B1 and temperature T1, and then we have M shaft power to the compressor, and at the outlet of this compressor we can have pressure. There is the function of the compressor is to raise the pressure, so the pressure B2 should be greater than P1 in this case, and T2 should also be greater than T1 in this case. This is in case of compressor, and the process in this case, inside this compressor, we call it compression process, because in this case the pressure is just increased in this case. The reverse of this, we can represent the turbine by this symbolic representation. In this case, actually, the flow is coming into this turbine, flow of high pressure, pressure B1 and temperature T1. This flow actually is expanding inside this turbine. Then we can generate actually, the representation of the turbine is the reverse. So this is actually the representation of the turbine. This is the turbine. The flow is expanding, then we can generate shaft power in this case. And the flow will be leaving at pressure B2, which should be less than B1, and temperature T2 less than T1 in this case. And the process inside the turbine, we call it actually as expansion process. So if I want to study this turbine or compressor, to study any open system, we have to draw, any open system is a control volume, so we have to draw this control volume around the system. This is the control volume, and look at actually the surface of this control volume, which we call it the control surface. And in this case, look at the masses and energies that are actually crossing this control surface in this case. And then we can apply the mass equation, as we have mass transfer open system. Then we can apply actually the mass equation in this case. This is a steady flow device, open system with single stream. We have single inlet and single outlet in this case. Then in this case, the mass equation will be M dot inlet is the same as M dot outlet or M dot exit in this case. So we can say, instead of inlet and outlet, we can just say 1 and 2. Okay, so we can say ρ1 A1 V1 will equal to ρ2 A2 multiplied by the velocity V2 in this case. Okay, density يا شباب is 1 over a specific volume. Because in a steam turbine, I don't have density in the table, but I have a specific volume in this case. And the M dot is equal to density multiplied by the volumetric flow rate. Volumetric flow rate is area by velocity. Okay. Like we can apply the energy equation as well. Then in this case, we have the whole of this equation. It will be Q dot minus work dot equal to M dot H exit minus H inlet. We call it H2 minus H1 plus V2 squared minus V1 squared divided by 2 divided by 10 to the power 3 plus G Z2 minus Z1 divided by 10 to the power 3. And this is the equation that we can apply for either for turbine or compressor. This heat transfer, we said, should be positive or negative depending on heat is added or rejected. Usually in case of turbine or compressor, usually they are adiabatic systems. We don't have heat transfer. But in some cases we may have some heat losses actually from the body of this turbine or compressor. Okay. So in this case, if it is given, then in this case, either usually it is rejected heat or something, then it should have negative sign. If he said we have some heat is added to the system, then you can consider it as a positive sign. And it could be adiabatic if it is adiabatic, insulated, isolated, or in most of the cases for steam, for turbine or compressor, just he will not mention actually or not talk about the heat transfer. So if it is not given or required, also we can consider it as 0, as we have explained earlier. Okay. And the work, it can be positive, it will be positive sign in case when we have turbine. The work will be negative in case when we have compressor or pump, or in case when we have fan. All of these devices are actually consuming work, so the sign of the work will be negative. This should be all heat transfer should be substituted in kilowatt. This is kilowatt, this is kilogram per second. and that should be kilojoule per kilogram from the figures. This term will be 0. This term first, that term will be 0 if not given. So if he didn't give you the change of elevation from the inlet section, the elevation between the difference in elevation between the inlet section and the outlet section, then in this case we can just neglect this term. And in most of the cases this term will be neglected in this case, if not given. This term will be neglected if not given as well. If not given, and also area A1 and A2 are not given. Because if he give you area A1, the area of the inlet section of the turbine or compressor, and the area A2, the inlet area and the outlet area, in this case, I have to calculate the velocity by applying the mass equation. So in this case, I will say m dot inlet will equal to m dot outlet, or rho 1 A1 V1 will equal to rho 2 A2 multiplied by the velocity V2 in this case. And in this case, the mass flow rate will be given in this case. And the density we can calculate actually in this case, the density, area A1 and area A2 are given. Then using the mass equation equating m dot to density by area by velocity, then we can calculate the velocity V1 and the velocity V2. So shabab, this term will be 0 if not given or required, and the area A1 and A2 are not given. But if he gives you the area A1 and A2, then in this case we can calculate V1 and V2 based on the mass equation in this case. Okay. So let's solve an example and see how we can apply the mass equation and the energy equation in this case. Okay. In case when we have compressor or turbine. Here is this is what we said is just a summary of what we said. Here in this example we have a compressor. So we have a flow compressor for air. For this compressor, actually air is coming into this compressor. So the working fluid is air. So I will be using air tables in this case. So the pressure B1 is equal to 100 kilopascal atmospheric pressure, and temperature T1 is 280 Kelvin, which is also the atmospheric temperature. We have input shaft bar to this compressor to run this compressor so that we can compress the air to pressure B2 is equal to 600 kilopascal, and the temperature T2 will equal to 400 Kelvin in this case. He said the mass flow rate of air in this case, m dot air, is equal to 0.02, yes, 0.02 kilogram per second. And he said while this process, there was some heat is rejected out of this compressor. This heat, he gives actually the value of the specific heat is 16 kilojoule per kilogram, not actually the rate of heat transfer. And we need to calculate in this case, required to calculate the power required to drive this compressor. We need to calculate here the shaft power required to drive this compressor. Okay. So in this case, what should we do? We have only two equations, mass equation and energy equation. In this case, mass flow rate is given, but actually area A1 and A2 are not given. So I don't need actually to apply the mass equation. So let's apply the first law of thermodynamics. Let's write it down again. Q dot minus work dot is equal to m dot multiplied by, let's say this is 1 and 2, H exit which is H2 minus H inlet which is H1. He didn't give actually the kinetic energy, and the area A1 and A2 are not given, so I will neglect the term of kinetic energy. And also we don't have the difference in high potential energy, it is not given, then in this case I will just neglect it as well. Okay, so this is actually will be the first law equation, can be reduced actually to this form. Type Q dot, this term, so let's substitute. Q dot is equal to m dot multiplied by a specific heat. Okay, and in this case we have mass flow rate is equal to 0.02 multiplied by specific heat in kilojoule per kilogram, which is 60. Now, M dot by Q, the unit here is kilowatt, minus the work required for the compressor, we need to calculate, equal to mass flow rate 0.02 multiplied by H2 minus H1. طيب, in this case, the working fluid is air. To calculate delta H, we have learned how to calculate delta H for gases. We have either two options, either to use actually the variable specific heat analysis using table from A17 to A25. Air actually is table number A17 in this case. Or we have the constant specific heat analysis. We can just say delta H will equal to CV average multiplied by delta T, and CV is calculated from table A to B in this case. He didn't mention actually directly in this equation, in this problem, which method I have to use. Then I will be using actually the variable specific heat analysis from table A17. So in this case, we can get H2 at temperature T2 equal to 400 from table A17. Then we can get the value of H2 will equal to 400.98. And also we can get H1 at temperature T1 is equal to 280 Kelvin from the same table, table A17. Then we can get H1. This is actually H2. H1 will equal to 280.13 kilojoule per kilogram. Then we can just substitute those two values. Then we can calculate the rate of work of the compressor. The rate of work of the compressor will equal to 2.74 kilowatt. When you calculate this value, you will have actually a negative sign. Negative sign indicates that actually this work is input to this compressor. This work is input to the compressor. Okay. So the solution here, Shabab, we just consider another way. We just say energy in will equal to energy out. I will add up all of energy in, and then I will add up actually all of energy out. Then in this case, we will calculate the absolute value of the work. Okay. I assumed here the work is in to the compressor and get the same sign positive. That means this work is in. So I have to understand that actually the sign is negative. But I do prefer actually to apply it this way. Q minus work equal to the change actually of energy transfer by mass from the outlet to the inlet. Then in this case, when you calculate the work, if it is added to the system, you will have actually the calculation resulting in a negative sign. Here in this example, we have here we said we have the power output of adiabatic steam turbine. So let's translate all of this, the power output of adiabatic. So adiabatic means the heat transfer is equal to 0. Steam turbine, so the working fluid is steam, and in this case the device actually that we are considering is turbine. So we'll apply actually the generated first law of thermodynamics that we have developed in case of turbine. He said the power output, we said the power output is the rate of work done is equal to 5 megawatts. Okay, let's look at the unit. This is megawatt, which is actually 10 to the power 3 kilowatt. And the inlet condition are actually expressed as shown in this figure. So let's look at this representation of a turbine. So we have a turbine. The inlet flow to this turbine, we have steam is coming at pressure V1 is equal to 2 megapascal. Please also be careful. This is megapascal. The values in the table, superheated table. I think in the superheated table it is in megapascal. Temperature T1 is 400 degrees C. And is giving also the velocity V1. Velocity V1 in this case also is given equal to 50 meters per second. And the elevation of the inlet section is equal to 10 meters. So in this case, the elevation Z1 is equal to 10 meters. Those are the conditions at the inlet section. And this steam actually is expanding inside this steam turbine to generate shaft power. This shaft power is given is equal to 5 megawatts. He said the pressure of steam at the outlet is equal to, so this is the outlet, so let's call it as 2. So B2 is equal to 15 megapascal, sorry 15, yes, kilopascal. And the value of the quality X2 is equal to, quality is equal to 90%, so X2 is equal to 0.9. So usually the steam after expanding in the turbine leave the turbine in the saturated mixture state. So usually it is saturated mixture, so the value of X is given in this case. The velocity V2 is equal to 180 meter per second in this case, and we have the elevation Z2 is equal to actually 6 meter to a reference base. So you can have an idea about the height or the size of the turbine, of a steam turbine. Here the elevation to a reference point is 10 meter, okay, at the inlet section from the top, and the outlet section from the bottom of the turbine is about 6 meters. So that means the height of the steam turbine is almost around 4 meters. Okay, so you can imagine the size of the steam turbine. Okay, so let's stop this. So we need to calculate, first of all, he asked us to calculate the value of delta H. We need to calculate delta H. We need to calculate also the change in kinetic energy. And also we need to calculate the change in potential energy, okay? And then we can compare actually the three values. Delta H is a change in kinetic energy and the change in potential energy, because we said in most of the cases we'll be just neglecting those terms in comparison to this term. So we'll see this. But let's calculate first of all delta H for this steam turbine will equal to H2, H exit minus H inlet, H2 minus H1. But in this case, H2, first of all at point 1, B1 is equal to 2 megapascal, and the temperature T1 is equal to 400 degrees C. Usually the steam at the inlet of the turbine, usually it is superheated steam, but we have to check. So in this case, we have pressure and temperature. I prefer to go to A5, table A5 with this pressure. Then we can get the saturation temperature. Compare the saturation temperature with the given temperature, as you know. So you will find in this case, the given temperature is greater than T saturation. And in this case, I have to use table heat, superheated table, which is table A6. To get the value, we need to calculate the value of enthalpy H1. If you calculate H1, you can get actually this value. H1 will equal to 3248.4 kilojoule per kilogram. Then you can get this value of H1. But what about the outlet section? We have saturated mixture. We have the pressure P2 is equal to 15 kilopascal, and the quality X2 is equal to 0.9. So directly with this pressure, I will be going to table A5. I need to calculate enthalpy H2, and the X is given, so I will get H fluid, the value of H fluid, and also the value of HFG from the table at this pressure. Then we can say just H2 will equal to H fluid plus X2 multiplied by HFG. X2 is equal to 0.9. We get H fluid and H gas. Then we can substitute actually to get the value of H2. It will equal to 2361 point something here, 0.01 kilojoule per kilogram. You can just check those values. So now we have the value of H1 and the value of H2. Then we can calculate the change of enthalpy delta H. So in this case, if you calculate delta H, which is H2, the exit enthalpy, the enthalpy of the exit steam, minus H1. So usually after expansion, the pressure is reduced, temperature also is reduced. So in this case, we expect the enthalpy to be reduced in this case. So H2 is less than H1, so this difference should be a negative sign. It will equal to minus 887 point something kilojoule per kilogram. So it is negative sign. Please be careful about the sign. So this is actually a negative sign. But what about the second term, the change in kinetic energy, which will equal to half V2 squared minus V1 squared. Usually all terms are actually in kilojoule per kilogram, and we said we have to divide this by 10 to the power 3. So in this case, just substitute. So 1 over 2 over 10 to the power 3 multiplied by V2 squared, which is 180 squared, minus V1 squared, which is 50 squared. This term, if you calculate in kilojoule, it will be 14.95 kilojoule per kilogram. Okay, compare this term, the change in kinetic energy, so the change of enthalpy. So it's a very low value as compared actually to the change of enthalpy. And that's why in most of the cases, this term kinetic energy will be neglected. So if the velocity at the inlet and the velocity at the outlet are not given, then in this case I will neglect this term. But if he gives you the area at the inlet section A1 and give you the area A2. So in this case, we can apply the mass equation. As I told you, we can say in this case, M dot will equal to rho 1 A1 V1 equal to rho 2 A2 multiplied by the velocity V2. If area A1 and A2 are given, then in this case, mass flow rate of steam will be given in this case, and we can apply the mass equation to calculate in this case the velocity V1 and V2. Then we have to calculate this term, okay? So if area A1 and area A2 are not given and the velocity is not given, then in this case, this term in the first law equation will be neglected. But what about the change in potential energy equal to G multiplied by Z2 minus Z1? We have to divide also by 10 to the power 3 to convert to kilojoule equal to G 9.81, Z2 is 6, Z1 is 10. Divide by 10 to the power 3, this value will equal to minus 0.04 kilojoule per kilogram. So you can see the value is less than 0.04 kilojoule per kilogram, so it's very low. So in all cases, actually, this term will be neglected, okay? The change of potential energy in this case. Type, he need to calculate also, in this problem, we need to calculate also the specific work out of this turbine. So he gives here actually the power, which is the rate of work done. But we need to calculate actually the specific work. Okay? So let's apply the first law equation in the specific form. Just divide the equation by M dot, so it will be specific heat minus a specific work will equal to delta H plus change in kinetic energy plus a change in potential energy. Okay? Adiabatic turbine, so we don't have heat transfer, this term is 0. So the specific work will equal to minus delta H plus a change in kinetic energy plus a change in potential energy. So that should equal to negative. We have calculated all of these values, 887 minus 887. Please be careful about the sign, plus 14.95 minus 0.04. You can calculate all of this. Then you can calculate the work. Will negative by negative will be positive. So in this case, we can calculate the specific work then. So the specific work here, if you calculate it, will equal to 872 kilojoule per kilogram. Okay. So in this case, he asked also to calculate the mass flow rate. We have defined the rate of work or the power equal to the specific work multiplied by mass flow rate. Or the specific work is equal to the power divided by the mass flow rate. Okay. So we have in this case power is equal to 5 megawatt. So we have to multiply by 10 to the power 3 to convert it equate to kilowatt. That should equal to M dot in kilogram per second multiplied by the work in kilojoule per kilogram, which is 872 kilojoule per kilogram. Then we can calculate the mass flow rate in kilogram per second. It will equal to 5.73 kilogram per second. Okay. And this is actually for the case when we have steam turbine. Okay. Right. That's all about when we have turbine or compressor. Then in this case, we can apply the first law of thermodynamics, the equations that we have developed for turbine or compressor. And also we have the mass equation. And then actually we can solve for the power output to the work output of turbine or the work input to the compressor in this case. And this is actually the first set of steady flow devices. We have another set of steady flow devices, which we call actually nozzles and diffuser. We talk about nozzle and diffuser. They have actually different application. Nozzle is mainly used in turbine. We said in turbine we have fixed blade plus the moving blade, and the fixed blade actually takes the shape of nozzle to accelerate the flow. So the main function of the nozzle is to actually accelerate the flow, to increase the velocity of the flow. Then we can have actually a velocity jet here to hit the bucket. Then we can generate shaft power from the moving blade of a turbine. And also we talk about the compressor, and we said in case of compressor, the design of the compressor, the blades, the area between the blades of the compressor takes the shape actually of the diffuser. So that actually when the flow is going inside the diffuser, In this case, area is increased, so the velocity in this case will be reduced, and the pressure will build up within the system. So this is in case of the nozzle. The main function of the nozzle is to raise the velocity or accelerate the flow. The main function of the diffuser is the same as nozzle actually, but in this case the direction of the flow is just reversed. In this case the area and the flow direction is increasing and the velocity will be reduced, and in this case the pressure will build up within the system. Usually the application of diffuser is applied in compressor. This is in case of compressor, and this is actually in case of nozzle. Is accelerating the flow inside turbine. And we said also there is application of jet engine, another application. We said jet engine, as we said, we have turbine, gas turbine, compressor and turbine, and here we have combustion chamber in between, and the gas is leaving the air or expanding inside the turbine. So the tail part of jet engine takes the shape of nozzle to accelerate the flow. So the flow here will be leaving those high velocities. That's why we have thrust force in the reverse direction. But the inlet section of the jet engine, if you look at the engine of the airplane or something, you will find the inlet section takes the shape of diffuser. So why shape of diffuser? So the area will be increasing, and in this case velocity will be reduced and the pressure will build up within the system. Because we need actually here the incoming air to raise the pressure of this air inside before it reaches the compressor. Then the compressor will continue raising the pressure of air to the combustion chamber pressure, so that we have exhaust gases here under high pressure and high temperature to expand in this turbine. Okay. Then we can generate shaft power to drive the compressor. Then the gases can complete the expansion inside the nozzle to have actually high velocity. Then we can have a thrust force in this case. So we have different applications for nozzles and diffuser. Okay. Right, let's have a symbolic representation. This is actually the nozzle, the representation in case when we have a nozzle. The flow is proceeding in this direction. So in this case, as the flow goes, the velocity in this case will be increasing and the pressure will be reduced in this case. Why the velocity will be increased, Shabab? Because when we apply the mass equation, as it is open system, so this is actually a steady flow, open system, single stream, we have single inlet and single outlet. Then if we draw a control volume here, this is the control volume. Look at the control surface, which is the surface of this control volume. Look at the masses in or out. Let's say this cross section inlet 1 and inlet exit 2. Then we can say actually M dot 1 or M dot inlet will equal to M dot exit in this case. Or we can say M dot in general will equal to rho 1 A1 V1 will equal to rho 2 A2 multiplied by V2. And this is actually the mass equation. But why the velocity is increased? Because this mass flow rate is constant. M dot 1 is M2, M dot 2 is constant actually at any cross section inside this nozzle. So at any cross section, if the area is reduced, then in this case the velocity will be increased in this case. So reducing the area will increase the velocity directly. But why the pressure is reduced? Because based on Euler equation, delta V minus rho V delta P, this is the Euler equation. We have negative sign here between the volume, between the velocity and the pressure. So pressure is proportional to 1 over the velocity. So when the velocity is increased, the pressure will be reduced in this case. Okay. But yeah, is this relation, in case when we reduce the area is reduced, the velocity will be increased and the pressure will be reduced. This in case when we have convergent nozzle. The area is reduced, you call this actually as convergent nozzle. Because actually, and this only applies for the subsonic flow. Subsonic flow when the Mach number, this is something additional, when the Mach number is less than 1. Mach number is the ratio between the velocity divided by the sonic speed, or the speed actually of sound. Okay? If the system, if the air, let's say air coming to the jet engine, to this airplane, if the airplane is moving with the velocity equal to the sonic speed, then we can say this airplane is moving with a sonic speed. Mach number in this case will equal to 1. Okay? In the case of nozzle, you look at this nozzle, this is a only convergent nozzle or subsonic nozzle. Usually the flow leaving this nozzle, you have a velocity less than the speed of sound. So if Mach number is less than 1, we call it actually subsonic flow. It has a velocity less than the speed of sound. This is actually the speed of sound. Okay. But in case of supersonic, Mach number is greater than 1. That is mean actually the system is moving with velocity greater than the velocity speed of sound. And in this case, we call it actually as supersonic. But in this case, actually, in case of supersonic, if we want this jet engine to move with a supersonic speed, we cannot use actually convergent nozzle because we have a relation that say actually that relates the change of area with the velocity and the pressure. We say delta area over area is equal to delta B over rho multiplied by 1 minus Mach number squared. Okay. I think that is the relation if I remember it correctly, delta B over rho V squared multiplied by 1 minus Mach number squared. Delta B over rho V squared. Okay. طيب in case if we have subsonic, Mach number is less than 1. So in this case, this term in case of subsonic, it will be positive. So that means in this case, the area is proportional to the pressure and actually proportional to 1 over velocity. So in this case, when the area is reduced, the velocity will be increased, and in this case, the pressure will be reduced in this case. But in case of supersonic flow, Mach number is greater than 1. In this case, actually, this term, 1 minus Mach number squared, this term will be negative. So we'll have a negative sign here. So that means the relation is reversed. So in this case, in case of supersonic flow, if I continue reducing this area, so that means actually the velocity will be reduced. And in this case, the pressure will be raised within the system. So if I reduce this area, in case of supersonic flow, Mach number is greater than 1. In this case, actually, the velocity will be reduced. It will not be actually supersonic anymore. And that's why in supersonic flow, we cannot use actually convergent nozzle. We use convergent divergent nozzle because in this case, in order to raise the velocity, we have to increase the area. So in this case, we use what's called actually the convergent divergent nozzle. The convergent nozzle here, in this case, as we reduce the area, the flow is still subsonic. In this case, the velocity will be increased. Until the throat here, the Mach number will equal to 1. The velocity will equal to the speed of sound. In this case, based on this relation, in order to have, if I continue reducing the area, the velocity will be reduced after Mach number equal to 1. But in this case, we have to increase the area in this case. And based on this negative sign, in this case, the velocity will be increased and the pressure will continue to be reduced in this case. And the flow, actually, the Mach number will be more than 1 in this case. So we have to increase the area in this case. This is convergent divergent nozzle, which is used actually in supersonic application. Okay? So what I want to say, Yani, in your mind, what you keep in mind is when the area is reduced based on the mass equation, in this case, the velocity will be increased. That's correct for the convergent nozzle for subsonic flow, when Mach number is less than 1. But in case of Mach number is greater than 1, that will be totally the reverse because of this negative sign. Okay? And we have to use convergent divergent nozzle. Okay? Like that is too much about the application, but I mean, it's good to know about it. Let's develop the equation. We have developed the mass equation, m dot inlet will equal to m dot outlet. Okay? For nozzle and also for diffuser in this case. Okay? This is the mass equation. Okay? And let's develop actually the energy equation or the first law of thermodynamics for nozzle and diffuser. So we have developed the general equation for a single stream steady flow. Q dot, we have developed this equation, Q dot minus work dot will equal to M dot multiplied by delta H, which is H exit minus H inlet, or we can say just H2 minus H1 plus V2 squared minus V1 squared divided by 2 divided by 10 to the power 3 plus GZ2 minus 0. And here also we have to divide by 10 to the power 3. Okay? In this case, if we look at this nozzle, or if we have diffuser, the diffuser is the same device as nozzle actually, but the flow is reversed in this case. This is actually what we call the diffuser in this case, and this is actually the nozzle. And to study this diffuser, to study any open system, we have to draw this control volume and look at the surface of this control volume, look at the masses coming in or leaving, and also the energy formed. Usually due to the dimension, small dimension of nozzle and diffuser, they have very small dimension. Then in this case, we can assume actually the system is a derivative. We don't have heat transfer in this case. But we just have flow here. Flow is accelerated inside the nozzle and decelerated inside the diffuser. So we don't have any kind of work. We don't have shaft work, electric, we don't have any kind of work. So work is equal to 0. But in this case, if you look at the inlet section, cross section 1, and the outlet section, cross section 2, they are actually at the same elevation. So in this case, we don't have a change in the potential energy. And based on this relation, we can reduce the first law of thermodynamic equation for nozzle or diffuser. It will be H1 minus H2 will equal to V2 squared minus V1 squared divided by 2 divided by 10 to the power 3. Why 10 to the power 3, شباب? Because the units here again will be kilojoule per kilogram in this case. But in this equation, شباب, the function of the nozzle is to accelerate the flow. That means actually V2 is much greater than V1. But here the function is to do what? Is to raise the pressure, and the velocity in this case is reduced. That means the velocity V2 for a diffuser is much less than V1. Okay, so that means V1 can be neglected as compared to V2 in case of nozzle. So this term can be 0 for the case when we have nozzle. Right. And this term, this is V1, and V2 can be 0 for the case of diffuser. V2 can be neglected as compared to actually V1 in case actually when we have a diffuser in this case. Okay. طيب اوكي شباب. طيب let's have this example. Let's say a very simple example. We have a diffuser. Here is passed in a diffuser in a jet engine. So we have in this case jet engine. So usually the diffuser in jet engine is actually representing the inlet section to the jet engine to raise the pressure of the incoming air. Okay. Right. So he said we have air, so we have to write down this. So the working fluid is air, and the air is an ideal gas. Okay, it's coming actually at pressure and temperature enter a diffuser. So the working device is diffuser. So in this case, we can use the equations that we have developed, the mass equation and the energy equations that we developed for the case of diffuser. In application of a jet engine, we said the inlet section of a jet engine is representing a diffuser. He said the condition here at the inlet of this diffuser, B1 is equal to 80 kilopascal, and the temperature T1 is equal to 10 degrees C. It seems this jet engine is in a kind of airplane flying at higher altitude, little bit medium altitude, so the atmospheric pressure will be 80 kilopascal, temperature is 10 degrees C. V1 here at the inlet of this diffuser is equal to 100 meters per second. So I think this is the velocity of the airplane, and the area A1 is equal to 0.4 meters. So those are the conditions at the inlet section. Okay. He said we have actually the flow is actually decelerating through this diffuser, and the pressure should build up within the system. And they said actually the velocity of the air leaving the diffuser is small compared to the inlet velocity. So in this case, V2 is much less than V1. We can say V2 in this case, we can understand that V2 is equal to 0. It can be neglected in this case. We need to calculate the mass flow rate of air and the exit temperature. Okay, but we don't have any equation other than the mass equation. So we have M dot, which is ρ1 A1 V1 is ρ2 A2 V2. This is the mass equation. We have the condition at section 1. So in this case, we can say M dot, which we need to calculate, equal to density by area by velocity at the inlet section. So how we can calculate the density? In this case, the working fluid is air. How we calculate the density? For air is ideal gas, so we have the ideal gas equation. But if it is a nozzle and we have steam, so density is equal to 1 over a specific volume. And for steam, we can use the steam table. But here we have air in a diffuser, So I will use the ideal gas equation, BV is equal to RT. In this case, he didn't ask you to use the compressibility chart, so I will be just using this equation, okay? Type BV, V is equal to 1 over density, or we can say density will equal to pressure over RT. Pressure V1 is equal to 80 kilopascal, we can leave it in kilopascal. R, which is the gas constant for air, 0.287, we can get from table A1 as well, you can check this value for air, okay? Multiplied by the temperature, it should be in Kelvin, which is 10 plus 273 in this case, okay? You can calculate this density. Density of air should be close to 1. It will be 1.015 kilogram per meter, okay? This is the density. Then we can apply here, then we can say m dot will equal to density 1.015 multiplied by area A1, 0.4, multiplied by the velocity V1, 200 meters per second. Then we can calculate the mass flow rate of air to this jet engine, 78.8 kilogram per second in this case. But we need to calculate also the exit temperature of this diffuser, okay? But the exit temperature, then we will use the energy equation to calculate the temperature. Right, let's apply the energy equation, the equation that we have developed for a diffuser. We said H1 minus H2 equal to V2 squared minus V1 squared divided by 2 divided by 10 to the power 3. And we said V2, he said V2 is much less than V1, it is 0. V1 is given and we need to calculate delta H. Right, delta H for air. Air is a gas. We learned how to calculate delta H for gases. We said we have constant specific heat and variable specific heat. For the constant specific heat, I need to calculate the average specific heat at the average temperature. But actually, the exit temperature is not given in this case. So in this case, actually, I will use the variable specific heat using table from A17 to A25. In this case, we have air. So air will stick actually to table A17. In your exam, I will not leave you actually with any choices. Just I will ask you to use directly the variable specific heat and mass. So using table A17 at temperature T1 equal to 10 plus 273, I think the temperature in this table is in Kelvin. Then we can go to table A17, we can get the value of H1. If you put the value of H1 in this case, it will equal to 283 point something kilojoule per kilogram. Then we can substitute here 283 minus H2 equal to V2, which is 0, minus V1, which is 200 squared divided by 2 divided, don't forget to divide by 10 to the power 3. Then we can calculate the exit ensemble. Exit ensemble H2 will equal to 303.14, okay, 0.14. Now in the table A17, at the temperature, he gave you the ensemble. So at T1, I got the ensemble H1. But in this case, at 2, we have the ensemble. Then we can go to the same table and we can get the temperature T2. So using H2, I will go back to table A17, then we can calculate the temperature T2, which will equal to 303 Kelvin in this case. Okay, so inshallah we'll continue next time with different devices. Okay.